Hello everybody, in this lecture we will be solving 1993 IMO problem number 6. Here is a view of this problem. There are n lamps arranged in a circle, and we recognize that we can index those lamps in mod n. As a result, each lamp at all times are either on or off. So in a binary status, it might be reasonable to think of on as 1 and off as 0 in mod 2. So we are considering it in binary. Perform steps starting from lamp L sub 0 and on a continual manner such that at step S sub I you operate on lamp L sub I if and only if, I should say, only if the previous lamp is on. Okay, and if that's the case, if the previous lamp is on by the end of the previous step, then we operate on lamp L sub I, and we turned it off if it is previously on, or we turned it on if it is previously off. Otherwise we do nothing, meaning that if the previous lamp L sub I minus 1 is turned off, we just skip L sub I. So initially all the lamps are on. Okay, so we would like to show three things. Let's start with the first one. There's a positive integer m sub n, such that obviously that integer will depend on the value of n, meaning depending on the number of lamps, such that after m of n steps all the lamps are on again. So we start with all the lamps on, and then after a few steps later we claim that they will be back to on again, and we want to inquire about this number. Okay, and then let's read through the second and the third part a little bit later. Let's play these games. The easiest way to think of this is obviously to play it. So let's consider the following. So arranged on a circle, L sub 1, L sub 2, we should have started from L sub 0. Sorry for that. So we are given 4 lamps, and the status of these lamps, if you guys are ready to play this game, so we know that we start with all these lamps turned on, 1 1 1, and here the game begins. Okay, we start with L sub 0. Do we operate on this lamp? Yes, because when we check the previous lamp, it is on. If it's turned on, the previous one, then we operate on the next one, so we turned it off. L sub 1, do we operate on this? No, because the previous one is off. Move on. L sub 2, do we operate on L sub 2? Yes, because the previous one is on, so turned it off. L3, do we operate on this? No, because the previous one is off. L sub 0, do we operate on? Yes, because the previous one is on, so change it to 1. Next one, operate. Yes, because previous one. Next one, operate. No. Next one, operate. No. Next one, operate. Yes. So this one is 0 again. Next one, operate. No. Oh boy. Oh boy. Okay, so I'm pretty sure we messed it up. Okay, let's do it again. All right. Come on. It always happens. Okay, I don't want to edit this video again, so you gotta bear with me. So I don't care how long this video will take. Okay, so let's start again. So all the lamps were on. All right, so start on L0. Previously 1, so switch this. Previous one off, don't switch this. Don't switch this one. Yes. No. Yes. No. Ooh. No. Okay, so check this out. No. Next one would be yes. The following one would be yes. The following one is a yes. Ooh, look at this situation. We are back to the... so let me use probably a different color. 1, 1, 1, 1. We have returned to the position 1, 1, 1, 1 after so many steps, right? So we wonder if that's general, right? So What if we do it 5 times? One thing that I would like to consider is the following. Even though this looks great, it's really messy because the numbers on a circle, they start messing up. And when I have 5 or 6 or so many lamps on a circle, that's not gonna be very handsome. So instead, I will come up with this new notation. Okay, so I'm developing my notation, right? So I have this is the initial probably. This is round 1, round 1, round 2, round 3, and so on. Round 4 if necessary, and I can go further if I need it. But this is lamp 0, lamp 1. This is the status of each of these lamps after each round of operation. L3, we decided to have 5 lamps. So this is the case where we have n equals 5 lamps. Let's see if we can play this game again. So at the beginning, everything was turned on. Okay, and we start by operating, S sub 0 here, we operate on L sub 0, check the status of the previous guy. So when I operate on L sub 0, let me change the color again. So we start from 1, 1, 1, 1, 1. Okay, so starting with L sub 0, check the status of the previous guy. Previous guy is L sub 4, right? So because this is around the circle, so therefore what do we do with this guy? Do we turn it? Yes, we switched it off. Then check the next guy. Do we change the status? No, keep it. Next guy, because the previous guy is a 1, I change the status to off. Next guy, I don't operate on this guy. Next guy, yes, I switched it off. The following guy, don't touch him. The following guy, don't touch him. The following, yes, because there's a 1 here, so make it a 1. The following guy, switch it. Following, don't touch it, don't touch it, don't touch it. Switch it, don't touch it, don't touch it, don't touch it, don't touch it. Okay, now this is the good start. Touch it. I mean, switch it, switch it, switch it. And I need one more line, so just give me a second. And round 5, so one of the guys has to go all the way to round 5, and guess what? Switch it again, and we are done. So check this out. The whole lamps now, as of the end of which move is this? So let's check. Let me count the number of moves. So we started from here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. After 21 operations, I performed these steps. After 21 steps, meaning I started with step S sub 0 and I went all the way to S sub 20. So it took me 21 steps, starting with S0 all the way to S sub 20, to come up with the situation all ones again, right? So we started with all ones, and we ended up with all ones again. So we can keep playing this game. If you guys want, I can quickly play this game with 6 of them, but I will do it in fast tuning, and you can check it for yourself with your own records. So because I really enjoyed this game, why not? So let me quickly do it again. 3, 4, 5, 6. So I have L sub 0, L sub 1, L sub 2, 3, 4, 5. We have the initial status, initial. Round 1, 2, 3, 4, 5. I think this should take me several rounds, so I'll be really fast. Okay, so please do it on your own as well, and check if our records match round 6, 7, 8, and so on. So let's see if I will need further rounds. Okay, so let's begin. I start with 1, 1, 1, 1, and get ready for fast tuning now. Yeah, so after these long computations, again, I just realized that I started with a sequence of 111s, and now all the lamps are turned on again, and it took me a mere 6 in each row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 60 plus 363 steps. It took me 63 steps to accomplish this goal. Okay, so now that more or less I'm confident on what's going on, it took me 10-12 minutes to figure this out, but now I'm more or less confident about attacking this problem on a more conceptual and general level. So how many steps will it take until it turns back on again? Obviously, this number of steps are variable, right? So here I couldn't keep track of it properly because at some steps I just switched the lamp, right? So I just jumped over the lamp because if the previous one was a 0, it requires you to jump. So I couldn't count it carefully here. But this tabling system enables me to count it carefully. And it looks like as the number of lamps increase, from 5, for instance, when we had 5, we had 21 steps. When we have 6 lamps, the case n is equal to 6, we ended up at 63 steps, and so on. So I assume the things will get even longer and longer. In fact, when you go backwards, we see some common themes on both endings. For instance, before an ending can happen, you should have at least one 1, and then a bunch of zeros following it, and then the next round finishes the game, right? So for instance, again, a 1 followed by zeros, and then the game is finished. And when you look at the previous step, you have 2 1s followed by zeros, right? And the same thing here, 2 1s followed by zeros. So more or less we have a grasp of how the game will end. In fact, the whole procedure is reversible. So something which is critically important, reversible, we can, or maybe I should say invertible, I don't know, reversible, invertible, whatever. The procedure that we are describing here will end up being reversible or invertible. It's crucial for understanding the game totally. But anyhow, so going back to our thing, so how can I make an abstraction of the whole thing? So let's consider that we are operating on lamp L sub j, and we decided that L sub j and L sub j plus n would represent the same lamp. With this convention in mind, I would say that the status of lamp j is x sub j. Now x sub j is either turned off or turned on, so it's binary, right? And we are told that we have operations, for instance, s sub j will affect, I think it's with an A, affect the lamp L sub j if L sub j minus 1 is 1. Therefore, I can express this English statement into a mathematical expression, meaning x sub j, the status will be the following. The status will be based on what we were previously. So this is the status of lamp j in the current round, and this is the status of lamp j in the previous round, right? Status of Lj in current round, and this one is the status of that same lamp of Lj in previous round. When I say round, I mean the rows of this table, right? So I'm counting which round we're at. And so x sub j is equal to x sub j minus n plus x sub, it depends on the status of the previous guy, g minus 1. Now, why is this true? So mod 2. Why is this true? Because if the previous lamp is turned on, it will have an effect. If the previous lamp is a 0, then it will have no effect on xj. So we will not operate on lamp j. But if it happens that the previous lamp is 1, then it will have an effect on the current status of our lamp. And that's the governing recursion rule for the whole procedure. That's it. So once you have an understanding of analyzing this thing in mod 2, writing down this equation. The rest of the problem is just technical details. Okay, so let's have a look at quickly these technical details. First of all, so this would require obviously that we need j greater than or equal to n, but then later on we realize that with the following convention, for instance, if by convention we let's write it in green. So if I think of this as the status x sub 0, so I can simply call this guy as x sub minus 1, this one as x sub minus 2, and so on. So therefore the status of this guy, the beginning status, is x sub minus n. So therefore in that case I would further extend this. So forget about this. We can even claim that j can start anything from 0, 1, 2, and so on, forever, right? So therefore, why? Because this recursion now is good. For instance, if I plug in j equals 0 in here, I get x sub 0 is equal to x sub minus n, but x sub minus n was 1, and the initial status, and so on. So therefore, the recursion will be still meaningful. So that's the first thing I will be doing. And as I said earlier, where let's make note of this, where x sub minus n is congruent to x sub minus n plus 1, all the way to x sub minus 2, x sub minus 1, and they are all equal to 1, meaning that all the lamps were on initially. Now, okay, so what's next? Consider the status of lamps at any given instant in time. Consider at time, let's say t. So time t is at the beginning of time t. So what is the status of each of the lamps at the beginning of time t? Well, the status, I can call it the status vector, right? The status vector would be the following. If you will, depending on what is the time here, for instance, at time 63, at the end of time 63, we would be in this status, right? So we have a clear understanding of this, right? But anyhow, so at time, at the beginning, let's say at time t, when I say time t is at beginning of time t, at beginning. So at the beginning of time t, our vector, status vector, will be the following. So the first lamp, well, depend on what lamp we are operating, right? So this is, how do I do that? Yeah, why not? Okay, let me just write it like this. So I'll just explain in a minute what I mean by this notation. Minus n plus 1, x sub minus 1, minus t minus 1, sorry for that, t minus 1. Okay, so what is this representing? So this is representing the status of the lamps at any given time, right? So therefore this is the status of lamp, because this is the beginning of time t, this would be the status of lamp t, right? So does that make sense? And so on. You have the status of the other lamps as well. So these are kind of the previous statuses of these lamps, right? So okay, so before they are being operated. So now we are about to operate on these lamps again. So for instance, just to make sense of it, v sub 0 would be equal to 1, 1, a bunch of 1s, because each of these lamps are 1, 1, 1. Now when you think about it, now this is a counting problem. How many different vectors is possible? Well, there are 2 choices for this guy, 2 choices for this guy, and so on, right? 2 choices for each one, and this is a vector of size n by 1 or 1 by n. Then in this case, this vector has 2 to the n different status vectors. Now my claim is the following: because in total we have, even though this number can be quite big, it doesn't matter as long as we keep applying this procedure, and as long as we don't fall into the situation where all of them are 0, this will go forever, and this will never happen, by the way. right? So our procedure is well defined. This type of case will never happen. So we will keep repeating this procedure over and over again, and this is kind of um, within 2 to the n steps, we are of course expecting to return back to the situation where all the lamps will be again 1 1 1 1 1. What if there's a situation where, suppose that the status vector at time j plus m is equal to the status vector at time j, and v sub j is the minimal one, it's one of the two n, but not this one. You might think, hey, we have a loop here, and maybe we will never visit 1 1 1 1 1 again. No, that's not gonna work. That's not gonna happen because, because of this thing. Because we know that all the procedures are reversible. So therefore, in a sense, you can multiply both sides by v sub minus j. So therefore, if this is the case, this should imply that these the vector should have, before this has happened, they should have met previously, namely at this level, right? Does that make sense? Oh well, in this case this is a t here. Sorry for that. Sorry for that. Let me rewrite this whole thing. Okay, so does that make sense? So let me say it again. So because the thing is reversible, so we know that if something like this has happened, v sub t has happened, then we know that before even this happened, we should have had this thing happening. So multiplying by v sub minus t. So this would have happened even before this guy has happened, right? Because our procedure, as I said earlier, is reversible. So like the logic that I tried to explain earlier, look at the end game. So end game can be reversed all the way to the beginning, right? And so on. So there is so this thing has a periodicity in a sense, right? It's periodic, this procedure. And this procedure being periodic, by the way, will help us solve the second and the third part. So therefore, the initial state 1 1 1 1 1 will repeat in at most 2 to the n steps, and usually those number of steps can be even lesser. For instance, let's check if our claim holds for the examples with. Unfortunately, we couldn't count it here, so forget about this case. But you can easily create the table here, right? So do you want me to create a table here quickly? I mean, I can do it, but I guess you guys can also do it too. L0, L1, L2. I was lazy to do it, but you start with 1 1 1 1. This is the initial, and then round 1, round 2, round 3. I don't think it will take too many rounds. Round 4, and so on. So you start with 1 1 1 1 1, then you will be 0 1 0 1. Then 1, because you changed the status here, 0 0 1, and then I think 0 0 0 1, and finally 1 1 1 1. I think, oh yeah, we don't even need this guy. So therefore, here we are done in 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. In 15 steps we are done here. Here we were done in 21 steps when n is equal to 5. So for instance, the upper bound on this one was, because we are n equals 4, 2 to the 4, of course this is less than 2 to the 4, makes sense. We want less than, I think, yeah, 2 to the n steps. So yeah, because 0 0 0 will never happen, so it should be less than 2 to the n steps. And this one is n is equal to 5. Obviously this is less than 2 to the 5, which is 32, significantly less. And this one is definitely less than 2 to the 6. We have n is equal to 6, which is, ooh, this one actually is very close. This gets me suspicious. And in fact, when now we turn into part B, ooh, wow, look at that. M of n is equal to n squared minus 1. For instance, when n is equal to n is equal to 6, n is equal to 6. Okay, so that one is pure coincidence, I guess. But let's look at the case where n is equal to 4. This one is reasonable. So when n is equal to 4, the guess is m of n would be 4 squared minus 1. Sure enough, we get 15 here. When m is equal to 5, for instance, if k is equal to 2, we have a 5 here. So 5 squared is 25. Let's see if we get exactly this count. So we have 5 squared minus 5 plus 1, 25 minus... what the... shoot. 25 minus 5 plus 1, 21. Woohoo! I am cool and hot. For 6 there is no rule, so I don't know why it ended up being n squared minus 1, right? So we don't know. But anyhow, so let's prove this one first. So if n is equal to in the form 2 to the k, then what happens? Okay, I will make use of my recursion. So we haven't used our recursion yet, so let's make use of this. So let me reproduce the recursion here again, and then let's solve part B. Recall. Recall from our recursion that x sub j is congruent to x sub j minus n plus x sub j minus 1 in mod 2. And right, so let's begin. So this thing is congruent to, we can replace each one with its using the recursion again. So meaning, for instance, x sub, if this recursion is true, it means that, for instance, let's do it here. X sub j minus n is congruent to x sub j minus 2, and the status before this guy in the previous round of the same lamp, plus the status of the previous lamp, j minus n plus 1. So what I will do is I will substitute this into here. So x j minus 2n plus x j minus n plus 1 plus, and for j minus 1 I will do the same thing, x j minus n minus 1. That's the previous round. Maybe I should write it like this, it's better. J minus 1 minus n plus the previous guy, j minus 2. But then I can organize it carefully so that I would get... did I do a typo already? I'm prone to typos. The previous, sorry for that. The previous is not plus 1, it's minus 1 here. Okay, sorry. So therefore I have xj minus 2n plus these two summing up 2 times xj minus n minus 1, and then the last guy, xj minus 2. And guess what? I can keep doing this stuff. Okay, so far I don't see any particular thing going on here, but when I repeatedly apply it, you will keep seeing new patterns here. So let me apply it one more time and the pattern will be obvious. So how do I replace this? This one becomes x this plus the one before that guy, the previous lamp is this one, plus 2 times this guy here. The previous round it was j minus 2n minus 1, and then the previous guy is x j minus n minus 2, and finally plus x, again the same thing. In the previous round it was like this, and the previous guy is, okay, so we have x j minus 3n, so we have j minus 2n minus 1, j minus 2n minus 1, we have 2 here, 1 more here, so plus 3 of them here, 3x j minus 2n minus 1 plus, and then we have these two, 3x j minus 2n, minus 2, minus, let's say minus n minus 2 plus, and then the last guy, xj minus 3. And guess what? I can keep moving like this. So I can repeat this procedure a long time. So I can stop after a few rounds. For instance, what happens after I repeat this procedure r times? So then x sub j after r times, this is the first time, this is the second time, and so on. After r steps, after r, let me not call it step, after r applications of the recursion, what do we have? X sub j. Okay, so do you see the binomial coefficients here? That can't be serious, but it is. So it turns out that this whole thing becomes like this. So after the jth step, it will become from I equals after the r steps. Sorry, after r steps, I equals from 0. Oh, not congruent. Equal to I is equal to from 0 to r. It would be r choose I times this crappy expression, and please make sure you confirm this, minus I in mod 2. Okay, right. Okay. So what I mean by mod 2 is I only care if this number, the coefficients are odd or even. I already know these are binary as well. And the same thing here. For instance, I can further simplify this expression by just replacing the 3's with 1's and so on. But then I here make a following huge claim. Oh, before the claim, obviously this would work only if this whole thing, j minus r minus I n minus I, has to be greater than or equal to minus n. So that's a condition when this holds, right? So, and now I'm curious what happens if after r applications of this recursion, what if I apply this recursion 2 to the k times? R is a power of 2. Then I claim that if r is 2 to the k, then I claim that all these coefficients are even, with the exception of the first guy and the last guy, which is always 1, right? So therefore, let's make the following claim. If r is in this form, then r choose I is even. Very simple claim. For I equals from 1 all the way up to r minus 1. It won't work for I equals 0 and r, because for I equals 0 and so that you will have just once. Okay, so why is this true? Well, we need to prove it, right? So I need to show, let's simplify this, show that r choose 1, r choose 2, r choose r minus 1, these are all even, where r is 2 to the power k. So proof. I just realized that the video has already been very long, so I will have to leave it to you guys as a homework. It's not too bad. Yeah. So it would take me probably about another 5 minutes or so to prove this whole thing, which maybe I can do an additional video later on. So let me cut this one short, but you get the idea. So all these will come out as even, but if that's the case, then we can rewrite this thing, right, as follows. So therefore this becomes x sub j is congruent to only the remaining ones, because even ones in mod 2 will be all 0, the first and the last term. So the first term will become x sub j, if here you plug in I equals 0, x sub j minus n minus wait a second, no, I equals 0, sorry for that, j minus rn plus, and then the last guy, when you plug in r, so j, this one will vanish, j minus r for r in the form 2 to the power k. But now I think I know how to handle it, right? So by the way, you need to have both of these greater than or equal to minus n, otherwise they will be ill-defined, right? So both of them are greater than or equal to minus n. Now I will do the following. Why don't we just take n equals 2 to the k? So therefore we can just simply replace r with n, knowing that n is of the form 2 to the k, which is exactly what the question is asking. What happens if n is equal to 2 to the k? So this is kind of a tricky business, right? So this question by no means is trivial. So I purposefully repeated this procedure r times, where r is 2 to the k, and now I replace r with n because I know that n is of the form 2 to the k. So therefore, as a result, what will happen here is therefore the boundaries still remain. So we still need j to be j minus r. R is just n now, so n squared, j minus n squared greater than or equal to minus n, and here j minus n greater than or equal to minus n. From this one you will get j is greater than or equal to 0. From this one j is greater than or equal to n squared minus n. So this one will probably be binding, this one will not be binding. But anyhow, so therefore our expression, so this expression becomes x sub j is congruent to x sub replacing r with n, so j minus n squared plus x sub j minus n. And now one more time I will apply the same procedure again on this guy, x sub j minus n squared plus this guy will become x sub j minus n x. Right. Yeah. Yeah, let's go back to the governing equation. So let me open an imagination box here. Remember, x sub j is simply equal to x sub j minus n plus x sub j minus 1. So the current status at the end of step j of lamp j would be the previous status plus the previous lamp status currently, right? So therefore x sub this guy would become x sub j minus n is just x sub j minus x sub j minus 1. Yeah. Okay. Let's move on. X sub j minus 1. Finally, these x sub j's would simply cancel out. Boom. So this would imply that x sub j minus 1 is congruent to x sub j minus n squared. So therefore, we can show the periodicity. So therefore, because it works for all the j's, as long as the j's fall into this interval, for all the j's, the periodicity would be, and what is the difference between j minus n squared and j minus 1? So let's say j minus 1 minus j minus n squared. J minus 1 minus j minus n squared is simply, the j's cancel out, n squared minus 1 as desired, right? So therefore the game will end in n squared minus 1 steps. That's really good. So finally, it's already time is, come on, part C. What happens if n is, quickly, n is 2k plus 1? We do the same trick. So all we do is n is equal to 2 to the k plus 1, but 2 to the k is, because it's r, we can just pick r is equal to n minus 1, right? And when we plug it into this, so it would be 2 to the k is r, so therefore r plus 1, right? So we still have j is greater than or equal to n squared minus no. J minus r is greater than or equal to minus n. So let's write that down. J minus rn. J minus rn is greater than or equal to minus n, and we decided to replace r with n minus 1, so that would imply j minus n minus 1 times n greater than or equal to minus n. Okay, so this is only holds for this case, which means j is greater than or equal to n squared plus n minus n, so minus 2n, only when this happens. Okay, let's go back to our expression. So in our expression, in this expression here, we will again plug in r, replace r with n minus 1. So therefore, x sub n r with n minus 1. X sub j is congruent to x sub j minus, replace r with n minus 1, n squared. So minus n squared plus. Let's just replace r over there. So r is just n minus 1 times n, and the other one here is j minus r plus x sub j minus r is just now n minus 1, so n plus 1, right? So therefore this thing comes out as, so this is simply congruent to x j minus n squared plus n plus x j minus n plus 1, and this is congruent to I'll do the same trick here. So that would be, so the first one, just leave it as it is, plus n plus, So yeah, let's just do some imagination here. X sub j plus 1 is congruent to x sub j minus n plus 1 plus x sub the previous guy j. So therefore this guy I can replace it with x sub j plus 1 minus x sub j. So x sub j plus 1 minus x sub j. Oh, okay. Did I mess up again? I hope not. Yes, I would like to say. But why do they not cancel out? Oh, I can cancel them out because minus 1 in mod 2, so we are investigating in mod 2, is the same as plus 1, so I can just switch the sign, right? Switch. So minus 1 is the same as plus 1, so therefore xj minus n squared plus n plus x sub j plus 1 plus x sub j, but then the x sub j's simply cancel out. So therefore this implies that yeah, let's switch at the same time. Let's switch also this guy as well, because yeah, minus would be better, so I can move it to the other side, right? So therefore we have x sub j plus 1 is congruent to x sub j minus n squared plus n. So therefore, because these two indexes, the difference will give us the periodicity because it works for all the j's, right? So that's awesome. So therefore which one is bigger? This guy is bigger. So j plus 1 minus j minus n squared plus n is simply equal to the j's cancel out, n squared minus n plus 1, and this is the desired result. Whew, so this has been quite a long video. The only part that I skipped is now at is this one, which feels terrible. So if you guys have time, I promise to shoot an extra video right now, so just give me a few minutes. I'll upload it. I'll give a link to this on the video, I hope. Okay, so alright, so let's stop the recording and hope you enjoyed the video.